So in this lecture we will talk about adjunction between two categories. So they are given two categories D and C, and we want to define what an adjunction would mean. So let us start with this. There are two categories. So this information has been taken from Wikipedia, so you must look at Wikipedia page on adjunctions. In fact, everything about category theory is given in Wikipedia, and it is always a good resource to look at it. So you're given two categories, and we want to define adjunction between these two categories. So first we will have to give two functors f and g. Say f goes from category D to category C, g goes from category C to category D. Now fix an object y in category D and an object x in category C. Apply functor f, you get fy. Apply functor g to x, you get gx. So you have these two arrows. In category D, you have an arrow from y to gx. In category C, you have an arrow from fy to x. So we say these two arrows have one-to-one correspondence. Yeah, or we have the following isomorphisms. So the arrow match up. So arrow y to gx match up to arrow fy to x. So you just have fixed objects y in D and x in C, and then just apply the functors. So if this thing is true, you say that f is adjoint to functor g. F is called the left adjoint and g is called the right adjoint. This is called the left adjoint and g is called the right adjoint. So again, this information is given on Wikipedia and you must read that page. Our purpose is only to give minimal introduction for algebraic geometry purposes. So now we want to again define adjunction, but in terms of natural transformations. So again you fix category D and a category C. So we have two functors taking category D to category D. Say 1D and other is first apply f and then apply g. Yeah, let me draw the functors again here so it is clear. So you first apply f, then apply g, you come back to category D. So we have two functors taking D to D. So you have a natural transformation between the two functors. This is called the unit of adjunction. Correspondingly, we have a co-unit of adjunction. Yeah, it takes fg to 1c. So there are two functors which take category C to category C. One is you first apply g and f and then you apply the identity functor, so you have two functors. Now these should satisfy the triangle inequalities. So this is how we write the triangle inequalities. You fix object y in category D, x in category C. Again apply functor f to y, you get fy. Apply functor g to x, you get gx. Draw the two corresponding arrows, name them g and f as I have drawn. Now you apply g to object fy, you get gfy. Now this is eta y, this is just precisely here, you have y here and then gfy. So yeah, eta y is, you just put y there in the above. What is this? gf to gx. This is just applying g to the arrow f. Similarly, this is fgx. Now fgx, this comes obviously from eta, not eta but epsilon. To epsilon you apply x and you apply f to the arrow g. These are all natural, you just draw it and you will see how it comes about. Yeah, so epsilon applied to x. Yeah, so you have epsilon will take fgx to x. So that is pretty much it. You know that natural transformations have to be evaluated on objects. So this is some sort of a these two are nothing but triangles or triangular identities. Now these are also written in another form, which is more common, and it is used a lot in category theory proofs. So for that, you fix an object X in the category C, and you fix this ID map from X to X. Now you apply functor G to it. You get Gx to Gx arrow. Now you would have, so from Gx to Gx. Now we need to have an arrow eta Gx here. Yeah, so if you apply eta Gx, you will get Gf Gx. So you have just replaced Y with Gx in the above diagram. Now coming to the right hand side. So just copy the above diagram down. You have X to Fgx. Again, this is epsilon X. And this to this epsilon X you apply G. So yeah, this arrow should point in the opposite direction. I'm giving arrow in the wrong direction. Oh no, arrow is in the right direction, sorry. So yeah, you apply G to it, you get G F G X to Gx. Yeah, so everything is correct. Yeah, so this is an ID map here. X to X is also an ID map. So similarly, we copy the same procedure again. You fix object Y in category D, you have the ID map from Y to Y. Obviously now we will have to apply functor F to it. First we copy the corresponding diagram. You have eta Y here and you have some map here, GFY to Y. Yeah, I'm just going to put a dot here because it is yeah. So you apply correspondingly Fy to Fy as an ID. So again you will have this map here. So you apply F to eta Y. So you will have Fg Fy and this map you will have, which will be eta F. So notice that it's just eta F because eta F just like demolishes this Fg. Fg just vanishes. So Fg has just vanished. So you go to Fy. So what is 1 written as? 1 is written generally as like this. You go G to GFG to G again. So notice that I've done nothing, just removed X from there. And what about 2? Now 2 is again clear. You go from F to FGF to F. So this is an ID. Number 1 is an ID and number 2 is also an ID. Now you need to practice how to write these natural transformations eta Gx and epsilon X. You apply X after, and how do you put functors F and G before it. So in this lecture we talk about examples for algebraic geometry. So we are going to write down examples which are particularly used in algebraic geometry, and there are a large number of examples given on the wiki page also. So you start like this. You have a category. Yeah, so I'm just going to write down first what are the categories, what is the left adjoint functor, and what is the right adjoint functor. So for other examples, you must see the Wikipedia page. So left adjoint F, this is in keeping with the convention we had on the previous slide. And the right adjoint functor, which is G. So our very first example, and in fact the most important example, is that between the tensor product and the homomorphism between modules. Now category D is modules over A, category C is also modules over A, Left adjoint is the tensor and right adjoint is the homomorphisms or the morphisms. This you must look at the proof of this in a good, it is given in every algebra textbook. For example, in a Dummett and Foote in the International Edition, this is theorem 43 in chapter 10. I don't know what it is in new editions, but you can always check for adjoint associativity in the index and it will lead you to the page. So in the International Edition, this is page 382, and it should not be that far away, and this was chapter 10, Introduction to Module Theory. Yeah, so this is, you have to read it because this actually covers all the important aspects of the arrows and how they behave. This is the most important example and you have to cover it. Understanding of that example basically gives you an idea of a correct idea of what adjoints mean and what is the correspondence of arrows. So that is why I have marked with it with the red star. So again, page 382 in Dummett and Foote. So again, you can do ring maps. This is again just extension of scalars, and you again have home or morphisms on the right side, but you know that it can also be written as a forgetful functor because you are going to the underlying sets. So now we come to the important example for this course, essentially is pre-sheaves on topological space, and then later on we will talk about sheaves. So we have pre-sheaves on topological space T, and then you have sheaves on topological space T. The sheafification is the left adjoint and forgetful functor is the right adjoint. So now we talk about sheaves or quasi-coherent sheaves. You have a morphism or a function, continuous function between topological spaces x and y. So notice the contravariance. So we will talk about sheaves on y and then sheaves on x. So we have the inverse image sheaf. This is the inverse image sheaf, and we have the push forward sheaf. So last we will define as the embedding. So you take a subset and embed it. Here we will have covariant functors because the way we will define sheaves. And we write this as like this, f underscore exclamation mark, it is called f shriek. And then you also have the inverse image sheaf.